7.6 Matrices and Simultaneous Equations. Our learning intention, how matrices can be used to solve simultaneous equations, and our success criteria, I can solve simultaneous equations using inverse matrices. So the textbook doesn't actually go into detail about this, but I'm going to show you how to create a matrix from a simultaneous equation. When creating a matrix from simultaneous equations, the first matrix is the coefficient of each term. The second matrix is a column matrix of pronumerals. So what does that mean? What that means is that we take the coefficient, so that's the number next to the letter, we put that into our matrix. So we're going to take the number 2, then 3, then negative z, or negative 1, and create our first row. On the other side, I'm going to put the number 7. Oops, probably not far away. Let's make it a little bit further. Number 7. Now, each of these coefficients are multiplied by a pronumeral. And that's x, then y, then z. So what I do is I put that into a column matrix on the side there. X, y, and z. There's my brackets around my first matrix. I then follow suit with the second row, and I use 3. Got a missing one there in a second, and I'll go into detail with that, and a number 2. So 3, leave a space, and 2. Because I don't have a term there at all, I would put 0. And then on the bottom one, remembering that if there is no coefficient, it's 1. So 1, 1, 1 down the bottom. So if a pronumeral is missing in an equation, then the corresponding matrix element is 0. So that's this guy here in the middle. And then the element in the matrix includes the corresponding operation. So just grab a highlighter. So I've got negative z there. So as a result, I still include that negative, and I make it a negative 1 there. Now, finishing off my my final matrix, I use these guys down the end here, 7, 2, and 7. And these are my matrices. They are formed from a simultaneous equation. So again, just taking all the coefficients, putting them into the first matrix, so that's all the numbers. Taking all the letters, or the pronumerals, putting them into the second matrix, a column matrix, remembering our matrix multiplication. And then our third matrix is after the equal sign, and that's all the solutions, or all the equation to the sums of the equations. So, example 15 from our text. Show that the matrix 5, 3, 6, 4 times xy is equal to 13, 16 generates the simultaneous equation 5x plus 3y equals 13 and 6x plus 4y equals 16. So what you first need to do is put this into, or laid out as it is. So we'll go 5, 3, 6, 4. I was about to say put it in matrix form, then realised it's already in matrix form. And 16. All right. So we need to remember our matrix multiplication. First of all, can we do it? So we're looking at a 2 by 2 times a 2 by 1. So because those two middle numbers are the same, I'm going to end up with a 2 by 1. All right, that looks right. So I multiply my first row by the first column. And I end up with 5 times x plus 3 times y. And that still gives me that very first term up the top here, or the first element, which is 13. Then I take my, I finished the first, I'm going to change colours there, we'll go yellow. I'm going to take the, I've taken the first row and the first column. I'm now going to take the second row, yellow is not quite bright enough, and I'm going to still keep taking that same column. I've only got the one column to take anyway, or wrong column. So I've got 6x plus 4y is equal to 16. Now I've still got boxes around these, or square brackets. So multiply the matrices on the left of the equation, keeping the matrix on the right unchanged. So this guy here is unchanged. This guy here we multiply. That was the challenging bit. Now the last bit, equate the elements. So what does that mean? That means take the first row in each matrix. First row in that one, first one in that one, put an equal sign in the middle of it and write it out. So 5x plus 3y equals 13. And then we do the same thing with the second row. So 6x plus 4y equals 16. So we're pretty much just removing the brackets. And that gives us, where's my red pen, our simultaneous equation over here. And it matches. So part B of example 15, solve the simultaneous equation using the matrix equation, showing all steps. Now I've just popped the one of the matrices there. So what you need to do is you need to use the square matrix. Whenever we're looking at solving simultaneous equations, we want to use the square matrix. So that's the 2 by 2 or 3 by 3, the square one. So first of all, we need to find our determinant. So remembering that the determinant is equal to AD minus BC. That's my A, B, C, D. So it is equal to 5 by 4 minus 3 by 6. Which is 20, take 18 equals 2. So my determinant is 2. The next step I need to do is find the inverse of the square matrix in the matrix equation. So again, we're using this same guy here. I need to find the inverse. So step 1 is the determinant. Step 2 is the inverse. So the inverse of 5, 3, 6, 4 is equal to, remembering we need to do 1 over the determinant, then we need to swap our A and D, so we end up with D and A, and we need to do negative B, negative C. So in this case, my determinant is 2, so I'm doing 1 over 2. My D value is 4, open my bracket, 4, my A value is 5. My B value is 3, I make that negative 3. And my C value is 6, and I make that negative 6 and put a bracket around it. Then what I do is I multiply through. I do a scalar multiplication. So I multiply this half out the front by every element in the matrix. So half times 4 is 4 on 2, which gives me 2. Negative 3 times a half is negative 3 on 2. Negative 6 on 2 gives us negative 3, and 5 on 2 is 5 on 2. Now again, I can move this into decimal form if I want to, but for the benefit of keeping my marks when I'm looking at further maths, I would recommend keeping it in, unless it specifies decimal, keep it in fraction form. Alright, next slide. Pre-multiply both sides of the matrix equation by the inverse. Now, I've copied the inverse up the top here. I'm going to put it into, you know what, I'm going to keep it as decimals. It's a little bit neater than what I'm going to be working with soon. So pre-multiply means the inverse goes first. So if you went back into, what is it, about 7.4, when we're talking about maybe 7.3, we're talking about matrix multiplication and summing matrices. Now with the summing matrix, they're the 1, 1, 1 kind of matrices. If we pre-multiply, it goes first. If we post-multiply, it goes second. And in this example, we're pre-multiplying. So we put our inverse, 2 negative 1.5, negative 3 and 2.5. This is all in the text if you're following along. And then I'm going to multiply it by the original, so this is the inverse. I'm going to change colours so that people can actually see what's going on. I'm going to pop down my original matrix of 5, 3, 6, 4. I'm going to just label a couple of them. So this is my inverse, and that's my original. And then we're going to multiply that by x and y. Now, I'm not changing anything, okay? I'm going to put my 2, negative a half, negative 3, 2.5, and 13, 16. What I've got is the only thing that I've changed. Okay, so that's the original square matrix. This is the original pronumeral matrix. This is the inverse again, and this is the original product. So I haven't added or subtracted anything, or I'll rephrase that, I haven't added anything that I won't be able to use. The original square matrix, the original pronumeral matrix, and the original product matrix is, hang on a second, I'm going to go back a page, go back 2 pages, my original sum from 2 slides ago. So that is my matrix, 5, 3, 4, 6, 4, 6, 4, I can't even talk tonight, with the pronumeral matrix and the product matrix on the end of it. And all I've done on both sides, so I'm still keeping that balanced, both sides, is added the inverse. The reason I did this is that a to the negative 1 times a gives us the identity matrix. So I can actually get rid of, oops, I should have gone highlighter. That's better. I can actually get rid of this, and I can write it like this. 1, 1, 0, 1. Oops, 0. So this is my identity matrix, where down that leading diagonal is 1s. Then I've still got my original pronumeral matrix, which is x and y. And I've got my, what is it? My inverse matrix. I've got the word written there and I still can't even remember. So I put square brackets around that, and 13, 16. All right, so and remembering that the product of any matrix multiplied by the identity matrix is itself. So anytime you multiply anything by this guy, you will still end up getting the original matrix. So this almost cancels it out. So x, y, and my square brackets is equal to 2 minus 1.5 minus 3 and 2. Oh my gosh, this pen's not loving me tonight. 2.5, 13 and 16. All right, so we have gotten our unknowns on one side, and we've gotten all of our knowns, or our coefficient matrices, on the other side. So now we just need to solve for this. So did I pop that up there? No, I'm going to write it out again. All right. I can't remember if I cut and pasted and put the matrix up there. No, of course not. It makes me write twice as much. Trying to keep my handwriting neat because I tend to get sloppy towards the end of the videos. So first of all, we need to find the product of the right side of the equation. So we want to keep these guys untouched. Oops. Can't even spell U-C-H-E-D, untouched, on that side. And then on this side, oops, I want to multiply. So I want to find the product. Find product, rather than just the product. Find product. So we multiply. So we keep our x and our y on the left-hand side. Then we multiply through. 2 by 13 gives us 26. And normally you would add them together. But because I've got a negative 1.5, I'm going to subtract. So 1.5 times 16 gives me 24 minus 24. And the second line, I've got minus 3 times 13, which is minus 39 or negative 39. And I've got 2.5 times 16 gives me 40. Add them together. And then that equals 2 and 1. So I have just a 2 by 1 matrix because remembering matrix multiplication, 2 by 2, 2 by 1. Yes, they match, so I end up with a remainder 2 by 1, which I have. So now we equate the elements to solve the simultaneous equations, and that just means, oops, that one, taking that, putting it in an equation. So x equals 2, y equals 1. That's it. So if you have any, if you can't seem to find a number that looks sort of right, stick it back into the original equation. So we had 5x plus 3y equaling 13. Just double check. You've done this with algebra. It shouldn't be any different with matrices. Substitute them in. 5 times 2 is 10. 1 times 3 is 3. 10 plus 3 is 13. If you'd gotten minus 4 as your x value, you plug it in, you don't get 13. You know you've mucked up somewhere. Take a few steps back and retrace where you're at. All right, on to example 16. For each pair of simultaneous equations, use matrices to find the value for E for which the equations do not have a unique solution. Okay, so the first things first. Write this out in matrix form. Remembering, E is my unknown, so in this instance, it goes as part of my square matrix. So my square matrix with wonky square brackets would be 7, 5, E, 5. Then I have my pronumerals, which are x and y. And then that's equal to 12 and 11. So I've just taken my coefficients, I've taken my pronumerals, and then I've taken the product at the end of it. So that's our first step. Second step, determinant. So we take our, again, square matrix, because this is where our unknown is. This is where we're trying to find our E. Remembering that A, D minus B, C is my determinant. In this case, my A is 7 times 5 minus 5 times E, which is 7 times 5 is 35 minus 5E. It is okay if your determinant has a pronumeral in it or an unknown in it, because our aim is to find it. So step 3 is let determinant equal 0. Then we can solve. So if I made, I'm going to change colours here so we can see the difference. Where's the nicer red? There we go. Let my determinant equal 0. That means that this is equal to 0. So 35 minus 5e is equal to 0. And then I solve for e. Remembering our algebra rules, in order to move this guy onto the other side, I add 5e to that side, add 5e to that side, and at the moment I've got 5e is equal to 35. Next step in algebra, I'm going to divide both sides by 5. So remembering whatever I do on the left hand side, I do have to do on the right hand side, and e is equal to 7. Oops, why have my heart? Oh, that's right. I was starting to worry because I had a magnifier happening there. All right, so e is equal to 7. On to the next slide. Part B. 11x minus 3y equals negative 9, and 22x plus ey equals 2. So I'm going to use the same concept that I've just used in the previous part of question 16. I'm going to go back to blue. Blue's nicer than red. So I'm going to write it in matrix form. Matrix form. So I've got 11 minus 3, 22 and E. And again, my pronumerals in this case are X and Y. And they are equal to -9 and 2. Here I'm getting a bit wonky again. Step 2, find the determinant. And the determinant is equal to AD minus BC, which is 11 times E minus -3 times 22. And simplifying all that, I've got 11E, -3 on the side times 22 equals -66. But I have an extra negative here, so it's going to become a plus 66. There we go. And then step 3, let determinant equal 0, solve for E. So we have 11E plus 66 is equal to 0. Make it easy here. I'm going to divide that by 11, divide that by 11, just to clean it up a bit. So I've got E plus 6 equals 0. Now I need to get one of them on the other side, so I'm going to move my 6. So I'm going to subtract 6 on both sides. E plus 6 minus 6 gives you E, and 0 minus 6 gives you -6. So in this case, our E value is -6. Alright, so that is it for 7.6. We'll be moving on to communication matrices 7.7 in my next video. Thanks.